Hello class, welcome back to another video. I hope everyone is doing well when they are watching this. Today we're going to be talking about chemical equations and how to balance them. So let's get started. So our objectives for today, or our goals, is to be able to compare our two types of chemical equations and also understand the symbols that are used in our chemical equations. And then we also want to be able to balance a chemical equation. So those are a few things that we're going to be talking about, and hopefully by the end of our video and the end of some of our work this week, we'll have this down very well. Some questions I would like to start by asking, though, is what are some other kinds of equations you've heard about? When you hear the word equation, what comes to mind? So just wanted to get you started thinking about that. I think of math equations when I hear equation, and so we are going to be drawing a lot of similarities from them. So what things are in a math equation? When we think about them, I like to think about some variables, maybe there's an equal sign, so maybe an addition or any kind of operator, addition, subtraction, multiplication, or division. Maybe there's some numbers, and if there is no number in front of a variable, we always assume that it's 1. So these are some of the same things that we're going to be working with in chemical equations. Luckily, thankfully, they're similar, and we can draw on our math knowledge to help us learn these. So I have a video I'm not going to show right now. I have it linked in our classroom, so please watch this. It helps talk through the basics of what a chemical equation looks like. But some of the important notes I drew from it is that there are, I should have said 2 main types. Let me change that real fast. Sorry about that typo. There are 2 main types of equations. Our first one is what is called a word equation. So this equation uses words for compounds, addition signs, and an arrow of some kind. For example, when we see methane plus oxygen with an arrow going to water and carbon dioxide, that is a word equation. Then we also have what's a symbol equation. These symbol equations are what we're going to be working with mostly. They use symbols for our compounds, numbers for phases, as well as addition signs and an arrow. So what does that look like? It looks like CH4. So CH4 in the gas phase plus 2 oxygen, O2, in the gas phase gets converted into 2 H2O, which is in a liquid phase, and CO2, which is a gas phase. So the same exact equation up here in our word equation looks like this as a symbol. When we have, for example, the CH4, that's saying that we have 1 carbon molecule with 4 hydrogen molecules all attached in that compound. So that is some of the notation. We have seen some of these before as we've gone throughout the year, but I just want to be very clear on what they look like. So when we talk about symbols in the chemical reaction, we're going to talk about the phases first. So each compound has a phase written next to it. When we see a little G, it means we're in the gas phase, an L in the liquid, an S is the solid, and then we have this thing called AQ, which is aqueous. So aqueous means that it's dissolved in water. So, for example, if we have salt water, I think I talked about this, yeah, it means that the compound is in water. So salt water would really be written as NaCl for salt aqueous, because it's all surrounded by water. Just to do a good reminder, we have 3 phases of materials. We can have, this is all just for water. When we have ice, that's water in the solid phase. So whenever we're getting ice out of the freezer, that's our solid phase of water. When we're drinking our water, that's our liquid phase. And then we also have a vapor or a gas phase. And this is when our air feels humid. When we boil water, we are changing it from our liquid to our gas phase. So our solids are very close together, very sturdy usually. Our liquids are always changing. Shape, I should say. They will fill whatever shape that they're put in. If we put water in a bowl and then transfer it to a glass, it will change shape based on what's around it. And air is very, very spread out as well. So those are our symbols. We also have some other symbols which are different arrows, have different meaning. So we're going to talk about our arrows now. A single-headed arrow means an irreversible reaction. And then they look something like this, while a double-headed arrow means reversible, and it looks something like this, where there's an arrowhead on each side. So these reversible reactions mean that they can happen both forward and backward. So if we look at our examples down below, we have CH4 and 2 oxygen makes CO2 and 2 H2O and energy. So we have a single-headed arrow. So that means we can only be going forward. It is irreversible, meaning that this side of the equation will not react to go back this way. But our reversible reaction means that it is constantly going forward by changing, this is showing a change of electrons. We're moving a bond from the right side to the left, and it can constantly go back and forth, meaning it's reversible. Most of what we will be working with is irreversible, but I wanted to explain what it would look like if we had a reversible reaction as well. So I got one more video to show you guys. This one's about balancing them. So we're going to be working with our symbol equations. We're going to be working with irreversible equations as well. And so this gives a very good example of how to count each one of the elements and then start to balance them. So again, that is linked in our classroom as usual. But here's kind of what I took from some videos is everything on the left side must equal everything on the right when we're balancing our equations. We can only change the large number in front of each compound. We can't change the small little subscripts next to the numbers. So for example, we might have C6H12O6 in a solid phase plus C6 oxygen O2 in the gas phase, which will go into 6CO2 in the gas phase and 6H2O in the liquid. So when we start talking about counting, we say everything must equal on the left must equal everything on the right. So what that means is that every carbon on the left has to equal the carbons on the right. So the way we know and can count our carbons is each one of these subscripts is telling us how many of this element there are. So C stands for carbon. This little subscript is saying that there are 6 of them. So when we come over to the right side, the only compound that has carbon in it is right here. And since there is no number below it, we assume it's a 1. So we have to place a large number out in front of it. So this large number will multiply by the small ones, meaning that 6 times 1, because there's no number here, we assume 1, is 6 as well. Then we can look at hydrogens. We have 12 hydrogens over here, and our hydrogen over here is H2. So to make sure we have 12 of them, we have to multiply the front all by 6. So hydrogens on the right now is going to be 6 times 2 to get 12. So we have 12 and 12. And then the same thing for our oxygens. The way this one works is we have 6 here, and then we also have this molecule that has oxygen in it as well. So we have 6 plus 6 times 2. So 6 times 2 is 12, so 12 plus 6 is 18. And that equals 6 times 2, 12, plus 6 times 1, which is just 6. So 6 plus 12 is 18 as well. So that is how we count our elements and that are part of our elements, and that's going to be very important as we start to balance these equations. So let's do one together. So this is the unbalanced equation we're given. We have KOH aqueous plus H3PO4 aqueous goes to K3PO4 aqueous and H2O. So as we start to do this, our first step is to count the amount of each element on the left and the right. So let's start doing that. On our left side we have 1 potassium, and we have 1 plus 4 oxygens. Our hydrogens is 1 plus 3, and our phosphorus, our P is 1. Now let's count them on the right. Our K is 3, our oxygen is 5, our hydrogen is 2, and our P is 1. So we've counted them on each side, and we can see that our oxygens and our phosphorus, our P and our O, are the same. But what's different is on our left side we need 2 more Ks, and on our right side, on this side, we need 2 more hydrogens, 2 more H's. So with our unbalanced equation, the next step is to find which compound to place our large number in front of. That's the only thing we can do to balance an equation, is change the number in front of each compound. So if we want to change our K's, the only compound on the left which has a K in it is this first one. When we're placing our large number in front, we have to do it where it multiplies to every part of the compound. We can't just place a small one down here. We have to multiply it all by multiply the whole compound by it. So K is the only one. If we need more K's on this side, we're going to have to multiply this compound, this KOH. So we need to get 3 K's on the left because we have 3 K's on the right. So we'll multiply it by 3 because 3 times 1 will give us 3. So let's place a 3 in front of it. Now we have a 3 KOH, and let's recount. So step 3 is to recount. That also, by placing a 3 in front, it changes our number of H's and our number of oxygens, the number of O's. So when we count the left side, we now have 3 K's and 3 K's, but we changed our oxygen number and our hydrogen number. So let's look at what we need. So we need the right side to have more oxygen and more hydrogen. So luckily we have a compound that has both of those. We have a compound that has hydrogen and oxygen in it. So what we would need to do then is figure out where to place our next number. Because we have a hydrogen and oxygen here, we can place a 2 in front of it because we need 2 more, for example, we need 2 more oxygen, or we need 4 more hydrogen. Either way, if we place a 2 in front of here, our equation will balance. So let's place a 2 in front of it and keep going through our steps. So step 5 then is to recount. Our left side is now at 3 K's, 7 O's, 6 H's, and 1 P, and our right side is the same. So we have completed and made a perfectly balanced equation. If we are continuing our recount and never get to them being the same, it is not balanced. So this is how we know we're done. Now I want you guys to try what what magnesium and oxygen reacted to make magnesium oxide would be like. So let's go through our steps. If you guys want to pause the video, please do, and do this, and then continue to see me go through them. So let's count. We need 1 more oxygen on our right side than on our left. So let's place a number in front of our one on the right, because the one on the right needs more. And let's recount. So now we have 2 magnesium, and we need 1 more magnesium on the left side of our equation. So let's place another 2 in front, recount, and we're all good. So our balanced equation would be this one. So I hope that it makes sense and that all goes easily. If you have any questions, please let me know.